before we left? Well, we just started this concept of continuity. Continuity of functions, and this is functions from the real numbers to the real numbers. Okay, so we introduced this last time. And the first kind of informal definition we had of it was where we say a function is continuous. This is at the bottom of page 36 in the notes. We say a function is continuous at a point A in its domain if the limiting value of the function as x, the limiting value of f of x as x approaches A, if that's actually equal to the value that it takes at A. So non-continuous behavior non-continuous at x equals A is some kind of picture which maybe looks like this. So this is an example of a function which is not continuous at a point A. The function is making a sudden jump in value, if you like, at the point A in its domain. And the limiting value of the function, well, there isn't even a unique limiting value of this function as x approaches A, because it depends whether you're approaching from the right or the left. It's got a different left-handed and right-handed limit. So that's an example of non-continuous behavior. So, we discussed this. We discussed this before the break. So, typical continuous appearance of a function f at a point A in its domain is just where the function is kind of smoothly or continuously changing through the point A. It's not making any sudden jumps. So our informal definition there at the bottom of page 36 says that the limiting value of the function as you approach A, as x approaches A, must actually be equal to the value that it takes at A itself. Okay, so as x gets closer and closer to A, these function values are getting closer and closer to the value that the function actually takes at A, f of A itself. Now, understanding limiting values of functions and continuity of functions, that's an important underlying concept that's going to underlie the notion of the derivative of the function, which we'll be coming on to shortly. So, just to give a flavor and some detail of the proofs and arguments that arise when you look at continuity, we're going to look at the proofs of a couple of properties of continuity. So these properties are over the page, and they're kind of familiar-looking properties in a way compared to things we've looked at, properties we looked at for convergence, limiting values of sequences and series, and limiting values of functions we looked at just before this. So the one we're going to focus on this afternoon is theorem 4.3 here, which says that continuity, this is continuity of sums, products, and quotients. So this is like an algebra of, it's showing how the concept of continuity fits with the algebra of functions. So when we introduced functions at the end of term 1, we stressed the point that functions should be considered as objects in their own right, which can be added together. You can take two functions and add them together to make a new function. You can multiply them together, take two functions and multiply them together, and you have a new function. Or similarly speaking, you can take quotients, divide one function by another, as long as you're avoiding 0 in the denominator. And well, the following theorem, 4.4, refers to a very important operation on functions, which is composing functions, running one function on the output of another function, composing functions. And continuity fits well with all of these operations. or another way to say it is that continuity is preserved by all of these operations. Now that means slightly different things in each case for each operation, but we're going to prove it now for some of the first operations. We're going to look at the sums operation and maybe the products one just now. Okay? And these are examples of the application of the formal definition of continuity. A kind of full-blown technical definition of continuity, which I think we just looked at once before Christmas. This is the formal definition on the following page there, on page 38. And so it kind of looks, it reminds us of the formal definition of convergence for sequences, in that it's got this term epsilon in it, and it's got another term delta in it as well. It kind of reminds us of that, and it's the same concept as we have in the informal definition. So the informal definition of the function being continuous at x equals a says that, well, the limiting value of f of x as x approaches to a, the behavior of the function as x approaches a, is getting closer and closer to the value of the function at f of a. And all the formal definition of continuity does is it attaches parameters to that kind of vague phrase of getting closer and closer to f of a as x gets closer and closer to a. So those two operations of x getting closer to a and f of x getting closer to f of a, the formal definition introduces parameters to kind of measure or express that degree of closeness. And it links the behavior of the two parameters together. Okay. So we'll have a look at the formal definition now, and then look at an application of it, proving that if continuity is preserved by adding functions together, taking linear combinations. So here we've got a bit of a sketch graph of a continuous-looking function. Here we've got the point A marked in its domain. And to say that the function is continuous at x equals a, what that says is, for any value of the parameter epsilon, now epsilon is measuring a radius of an interval around the value of the function, f of a. So for any size of interval around the value of the function f of a, this L here is representing f of a on the vertical axis. For any size of interval around f of a, there exists a certain size of interval delta. Delta is measuring the size of an interval around point A in the domain. So for any size of interval around f of a in the codomain, there exists a size of an interval around A in the domain. And the property that that delta has is that if little x is any argument inside this interval here, if little x is any argument within a distance delta of x, so this inequality here, x minus a being less than delta, in terms of the graph, what that says is that x is inside this little interval here around a. Well, if x is inside this interval here, delta, the property that delta has is that if x is inside this interval, then the value f of x lies inside the epsilon interval around x. So the way the formal, you see, because x minus a being less than delta implies that the absolute value of f of x minus f of a is less than epsilon. This inequality here, absolute value of f of x minus f of a being less than epsilon, what that means is that f of x, the point f of x, lies somewhere in this interval on the y-axis around the point f of a. It's important to see the way the two parameters are arranged there, quantified in that formal definition. It says for every value of epsilon, for every positive value of epsilon, there will exist a corresponding delta. So the order in which they appear at the start of the predicate statement and the way they're quantified is important. So no matter what value of epsilon is given, and the issue is as epsilon gets smaller and smaller, no matter how small you make epsilon, you can always find a corresponding delta here. And the idea is that as epsilon gets small, the delta will probably have to get small as well. If you're asking for the values to be very close to f of a, you're probably going to have to go quite close to a in order to make it. So no matter what value of epsilon you're given, if the function is continuous at a, it must be possible to find a delta which has this property here. The property is expressed in terms of this implication between inequality statements. The absolute value of x minus a is less than delta. If x is lying in this interval here, that implies that f of x is lying inside that interval on the y. So that's the formal definition of continuity. So let's look at an application of it now. These are examples of application of the formal definition of continuity to proving some properties of continuity. In the first property we're going to look at is one part of theorem 4.3. So we're going to look at theorem 4.3 for linear combinations. So we'll carefully state what that is now. I mean, it's stated in theorem 4.3 as it is in the notes. Yeah. Okay, so here's the proof of it. So we assume that functions f and g are both continuous at x equals a. Okay. F and g are two functions that are continuous at the point x equals a. We let alpha and beta be any two real numbers. These are going to be the coefficients in the linear combination of functions that we're going to construct. We will now prove that alpha f plus beta g. So alpha f plus beta g is a new function. Okay? The linear combination of two functions f and g. It's potentially any linear combination. So I haven't placed any extra conditions on alpha and beta. I've just said they're two real coefficients. We will now prove that alpha f plus beta g is also continuous at x equals a. Now to do this, we're going to have to prove that the formal definition of continuity, which you can see here quoted for a function f, we're going to have to show that that holds for the new function alpha f plus beta g. Okay? I'm just giving lots of explanation here for how we set this up. So to do this, we need to show that definition 4.3, isn't it? Definition 4.2, formal definition of continuity, that holds for the new function alpha f plus beta g. So you're seeing here examples of how an important aspect in mathematics and pure mathematics and in establishing the theory of these concepts is it's very much in constructing careful, strict, complete logical arguments. Not so much about calculation with lots of numerical quantities, but rather careful treatment of the definitions and showing how the definitions combine with operations that you define, and how properties are preserved. So, let's see, the formal definition says for every epsilon, it must be possible to find a delta. What we do is we let epsilon greater than 0 be given. So we consider a positive value epsilon, and now we have to find the delta. Now I won't just magic it out of thin air. First of all, we'll look at we'll look at the inequality that the delta has to say something about. Okay? So first we examine the absolute value. First we examine the absolute value. What absolute value appears on the right-hand side of the implication? The absolute value of the function minus f of x minus the value of the function at the base point A. But now we're here focusing on this new function, alpha f plus beta g. So it's this absolute value here we have to focus on. We have to find the delta such that if x is within a distance delta of A, this absolute value has to be less than epsilon. So we want to make this absolute value, we want to make it small. We want to control the size of it. How are we going to control the size of this absolute value of differences? Well, the difference inside, you see, is made up of differences involving the functions f and g. You just need to see that clearly, how this absolute value depends on absolute values involving the function f on its own and absolute values involving the function g on its own. We've assumed that the two functions f and g are continuous, so those absolute values we'll be able to control, and then ultimately control the size of this. So we need to, first of all, we'll re-express this. We'll re-express it by applying the definitions of the operations of scalar multiplication of a function by a coefficient alpha and beta, and what it means to add two functions together. Well, all of this can be reorganized as, well, let's just expand these brackets first of all. So this is alpha times f of x plus beta times g of x minus alpha times f of a minus beta times g of a. So all I've done there is apply the definition of what it means to add functions together and take scalar multiplication of functions. Alpha f plus beta g evaluated at x is simply alpha times f of x plus beta times g of x. And then I can gather all the f's together, factorize out the alpha, and separately gather all the betas together. So I can now write this as alpha times f of x minus f of a plus beta times g of x minus g of a. Now this is good because I'm taking my original absolute value and now I'm starting to see how it's made up of something depending solely on f and something else depending solely on g. And then a crucial step here then is in applying the triangle inequality. Okay, we mentioned the triangle inequality last time before Christmas. And this allows us to say, Now we use the triangle inequality. Triangle inequality that says absolute value of A plus B is always less than or equal to the absolute value of A plus the absolute value of B. And we also use another property of absolute values, that if you have a scalar, lambda times A, well, that's going to be equal to absolute value of lambda times absolute value of A. So the absolute value of a product is the product of the absolute values. So I can take this out now as absolute value of A times absolute value of f of x minus f of A plus the absolute value of B times absolute value of g of x minus g of A. So remember, what we're engaged in at the moment is we're trying to prove that the formal definition of continuity holds for the new function alpha f plus b. This formal definition, the crucial part of it, we need to show that we can satisfy this inequality here with a suitable choice of delta. So in our case, it means we have to control the size of this absolute value at the top of this page here. The absolute value of the difference of the value alpha f plus beta g at x and its value at A. What we've done with this algebraic manipulation and triangle inequality is we've shown how the absolute value that we're interested in at the top is bounded above, is less than or equal to this absolute value plus this one over here. And both of these we can control. Okay? Because we're assuming here that the function f is continuous at A, and so is the function g. And if f is continuous at A, it means you can control the size of this. You can make this less than anything you want. And you can control the size of this absolute value g of x minus g of A as well. You can make that as small as we want. Okay? Both of these can be made arbitrarily small, you can say, since f and g are continuous. Right, so that since f and g are continuous at x equals A. Okay, so now we want to hit the nail on the head. Now we want to show exactly what we mean. We know that there exists a delta 1 bigger than 0, such that if x minus A is less than delta 1, this is going to imply that absolute value of f of x minus f of A strictly less than, and I'll choose epsilon over 2 times the absolute value of alpha. See why I've chosen that, so that when I substitute it in here, I'll multiply it by this absolute value of alpha, and I'll be left with epsilon over 2. Choose a similar thing for this one over here, so I'll be left with 2 epsilons over 2's. When I add them together, I get epsilon. So this is true, you see, because here I'm just using, what I'm doing here is using a special instance of the continuity of f at A. The value of epsilon I'm using is this new value, epsilon over 2 times absolute value of alpha, but that's just some positive number. And I know, because f is continuous at A, I know that there exists the delta 1, which makes this implication work. Similarly, there exists the delta 2, such that x minus A being less than delta 2, that makes the absolute value g of x minus g of A strictly less than epsilon over 2 times absolute value of beta. But now we've got 2 values of delta floating around. But But I want to only talk about one value. See, if I take the smaller of those two, the delta 1 and delta 2 are two positive numbers. They're both talking about sizes of interval around x equals a. So if I just take the smaller of those two, then I'll know that both these conditions here are true. Okay? And so both these implications. And now we take delta, the delta we need to exhibit, we take this to be the smaller of delta 1 and delta 2. Just whichever one is small. And so if x minus a is less than this delta value, then both so these inequality, I'll call this inequality 1, this inequality 2, and both 1 and 2 hold. So if x minus a is less than delta, then the absolute value of alpha f plus beta g evaluated at x minus alpha f plus beta g evaluated at a, this will be strictly less than, because I know that this alpha f plus beta g evaluated at x minus alpha f plus beta g evaluated at a, this is what I looked at up here, and I know that this is bounded above by this expression here. In fact, this expression here. So this is strictly less than absolute value of alpha times epsilon over 2 times absolute value of alpha, plus absolute value of beta times epsilon over 2 times alpha. And see this, when you clear the alphas and clear the beta, this just comes out as epsilon. So, sorry, a little bit squashed up there. So this here is alpha f plus beta g, just that linear combination I've been writing all the time. See, what we have there at the bottom of the page, you should look at that now and compare it back to the formal definition of continuity. And you'll see it's exactly what we need. It's exactly the formal definition of continuity. We started off the argument at the top of the page with any epsilon, any positive value of epsilon. Down here is where we found the delta. So the delta does exist. The minimum of the other two deltas, which exist because f and g are continuous. But this delta has this property here. If x minus a is less than delta, then the absolute value, the difference of the function at x and the function at a, is strictly less than epsilon. And that's exactly what the formal definition says there. The absolute value of the function evaluated at x minus the function evaluated at a is strictly less than epsilon. So this last statement is the formal definition. This is the definition of continuity. And so the result tells us. Okay, any queries about that, or any further clarification of the query on any of the steps there? This moment. this moment. I mean, it is something that you should return to and look at in detail and try and appreciate the way the formal definition is operating. Try and track step by step how it's taking that definition and assembling the fact that the definition holds for F on its own and the fact that it holds for G on its own, how those two assumptions are put together to show that it holds for alpha F plus beta G. You should also compare this with the proof of convergence of linear combinations of sequences. So compare this with the proof of convergence of linear combinations of sequences. Okay, something we did in the kind of very middle part of term 1. It's not exactly the same, but when you compare this argument with that argument back then, you'll spot similarities. It's the same underlying technique. It's working with a slightly different formal definition, because in the first one we're dealing with sequences, lists of numbers that converge to a limit. Here we're dealing with functions defined as the real numbers and their continuity properties. But the kind of underlying structure of the argument is the same. Compare this with the proof of convergence of linear combinations of sequences to see the same structure of the argument. This is one aspect of mathematics that's quite important as you work through it. You'll see lots of arguments in lots of different contexts, but you should always be alive and be aware and looking for similarities. Okay? There are many places where an argument to prove a property in one situation is more or less following the same lines of an argument in maybe slightly different contexts. Okay, I don't want to rush things too much, but this afternoon, I'll be taking the lecture this afternoon, because I took my usual one yesterday. So this afternoon we'll look at similar proof, but this time for products. Okay? So this afternoon we'll consider products. Consider products and maybe compositions as well. And after we've done a bit of, just a little bit more work with this formal definition of continuity, we'll then be in a position to move on to beginning our formal work with the derivative, the definition of differentiation. Okay. So I will see you again just in C014 an hour for that second lecture, and I'll see some of you for the tutorial this afternoon. Remember, those of you in Frank's group, who go along to Piotr Walczyk's tutorial. Yeah.